Okay, I think it's recording. Do you guys, I guess you see all these buttons on your screen too, right? Just move them over so they're out of the way. All right. Okay, so what is the probability distribution? It shows the probabilities of all possible outcomes of an experiment. How do you show it? Does anybody know? It's two options. You can show it as does anybody want to, let's try to do this a little bit more interactively so you can unmute yourself. How can you show a probability distribution? Okay, well, you can do it as a table or you can show it visually as a graph. Let's do both of them, okay? One question first. What happens if you add all the probabilities of all the outcomes? It has to sum to 1, okay? Right? Probabilities always range from 0 to 1. If you add up all the possible outcomes, the probabilities of all the outcomes, it has to add to 1. All right. Okay, example. Determine the probability distribution for the sum rolled with 2 dice. So first of all, what's the sample space, the number of possible outcomes? So we can have it a 1 and a 1 to get a sum of 2, and you get a 6 and a 6 and you get a sum of 12. So you can get every number in between, right? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. And to do this properly, you would probably have to make a table, but I think you've done it a few times by now. What's the probability of getting a 2, a sum of 2? You guys, so there's only one way to get a 2. It's a 1 and a 1. But how many outcomes are there when you roll 2 dice? You have 6 outcomes for the first dice and 6 outcomes for the second dice. So altogether, you have how many combined totals? Combined 36. So there's only one way to get a 2, and there's 36 ways of rolling 2 dice, right? So it's 1 out of 36. You guys, how many ways can you get a 3? So these are all going to be out of 36, right? How many ways can you get a 3? So you can get a 1 and a 2, or a 2 and a 1, right? So there's 2 ways to get a 3. How many ways can you get a 4? 3. You can get a 1 and a 3 or a 1, or a 2 and a 2. How many ways can you get a 5? Looks like there's a pattern there. So it's 1, 2, 3, it goes up by 4, and then 5. And then, what about an 8? Would it be 7 out of 36 if you continue the pattern?
It'd be 5.
It'd be 5. It goes back down, right? Because there's only one way to get a 12. It's 6 and a 6, and then it goes. So it goes up to 6 and then down to 5. So this is a probability distribution, and when you do a probability distribution, your variable is your outcomes are, we'll just call them X, and the probability is going to be P, like probability of outcome X. All right, so X are the individual outcomes. So as a graph, we can show a probability distribution too. So this is as a table, and now we're going to do it as a graph there. Let's put outcome 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Those are the outcomes, or the sums. Okay. And here we'll do the probabilities, because that's what we're doing a distribution, so we have to show probabilities. Probability. And what's it going to go? We'll just leave it as fractions. So it goes from a low of 136 to a high of 636. So 136, 236, 336, 436, 536, 636, and that's it. All right. So it's pretty easy to show this information on a table. As a graph. The probability of getting a 0 is 0. There's no way you can get a 0. The probability of getting a 1 is also 0. They don't show up as the outcomes. The probability of getting a 2 is 1/36. So we can just kind of draw a line like that. Probably getting a 3 is 2/36. A 4 is 3/36. A 5 is 4/36. A 6 is 5/36. A 7 is 6/36. An 8 is 5/36. A 9 is 4. A 10 is 3. 11 is 2. 12 is 1. So if I ask you for a probability distribution, it's either give it to me as a chart, a graph, or give it to me as a table. All right. Are we good? Okay. So is everyone seeing this okay?
Yes.
Okay. All right. So just some definitions here. A random variable, x, so we're going to call the variable with an uppercase. Okay. Has a single value denoted x, like that's the actual outcome. We call the variable capital, typically call it x, capital X, and the outcome is a lowercase, small x, is each outcome. So in example 1, the random variable x is the sum of 2 dice. So this is x, and then this is going to be p of, and probability is going to be the individual outcomes. Okay. All right. Let's look at 2 types of variables. One's discrete, one's continuous. Does everyone know what discrete is? Can somebody tell me what the blank would be? Discrete random variables have blank values. Okay, let's go with continuous. Continuous random variables have an blank number of outcomes along a continuous interval. So what would be the blank there? Well, you guys are all kind of shy, but this would be an infinite. Okay, if it's continuous, it can have an infinite range of outcomes. So if it's not infinite, if it's discrete, it's the outcomes are separate. Now, a lot of times people think that this has to be integer values. It doesn't have to be integer values. It's often integers, but not always. Okay, so just a little, some examples. Classify each of the following random variables as discrete or continuous. The number of phone calls made by a salesperson. Is it an infinite number of outcomes, or is the variables, does it have separate values, or are they continuous? So that would be discrete, obviously, right? It's discrete because a sales rep can call 1 time, 2 times, 3 times, 4 times, 5 times, but he can't call 5.5 times, or it's an integer value. The length of time the salesperson spent on the telephone would obviously, so I need some help here. Just yell it all out. So the answer for the second one, B, would be maybe 1 person yell it out. You can spend 2 minutes and 30 seconds on the phone. You can spend 2 minutes and 31 seconds on the phone. You can spend
Continuous.
Yeah, that'd be continuous. All right. The company's annual sales. Oh, this is kind of interesting.
Would it be discrete? I mean, no, continuous.
Yeah, well, how do you measure sales?
The amount of...
It's money, right? So money,
yeah.
Is money continuous? Like you can have $10.15. Can you have $10.15.5? You can't, right? It's either $10.15 or $10.16. So
Also be discrete.
it would be discrete, right? Because you can't have. It's not. They are separated. It's not an integer value. It's pennies. They're discrete by pennies. So that's as far as it's. It almost looks continuous, but if you can't go any. The way money works is you can't go. You can't chop up pennies. The number of widgets sold by the company would be. So number of widgets is just a thing. So you're counting things. So that's going to be an integer, right? You can't make half a wheelbarrow. The distance from the Earth to the Sun. It's not constant, by the way.
That's discrete.
What's that?
Is it discrete?
No.
Oh.
So the Earth actually,
Continuous.
it's continuous because it varies a little bit. It's not. The Earth doesn't go around the Sun in a perfect circle. It goes around in an ellipse. Does anybody?
So discrete is when it's perfect, like when it's whole numbers.
Yeah, either whole numbers or at least the values are separated. It doesn't have to be integers per se,
Okay.
but there's a sort of separation. But the Earth can be 92 million miles away from the Sun, and then it could also be 92 million miles and 1 inch away from the Sun. It could be. It's just continuous. It's not discrete values.
Okay, and the next one is discrete.
The next one's discrete. Yeah.
I got it right.
All right. Can we flip the page? I think the trickiest one is this one, because
That.
the pennies
Okay.
make it discrete. You can't chop it up anymore. Okay, let's flip it over. Oops, there's nothing there. Hold on. Where's my next page?
Oh no.
All right, let's get into a formula. Oh, wait a second. There we go.
So is that the other page? When I
Yeah.
printed it out this too. Oh wait, let me camera's out.
Is that page 2? Is that what you got for page 2?
Yes.
All right. So, I want to define something called expectation. Let's do an example. I'm gonna put the formula here. If you can write really small, I'm gonna write some stuff up at the top. Okay. Let's do an example. So, does anybody? When we did that little summary, that little correlation assignment at the very beginning, we designated the mean with a certain variable. How did we recall the predicted average is the same as the mean, right? Average is the same as mean. Expectation is the same as the mean, but it's of stuff that hasn't happened yet. So the mean is an average of stuff that you have values for it. Expectation is the mean of stuff that you haven't done yet, but if you run the experiment a million times, it would be the average of what you're expected to get, right? So, or the mean of what you're expected to get. So, remember what the mean was? Like what variable we called it? Does anyone remember this? We called it X bar. No. Anyway, that's what I mentioned that the mean is. So the mean. I won't call it X bar. We'll just call it mean. The mean equals. How do you get the average of something? What's the formula for getting?
You add them up and then divide it.
By the number.
So that's going to be you add up all the things.
So I got it before you.
And so adding stuff up is we'll call it we'll use the letter sigma. Sigma just means sum of all the values, right? And you're dividing it by the total number of things. So let's do an example. Let's say we have the values 1, 1, 1, 6, 6, 6. Okay? Let's find the average of those. So the mean, we're going to call it X bar, X with a bar over it. So the mean is going to be, add them all together, it's going to be 1 plus 1 plus 1. Sorry, plus 6 plus 6 plus 6. All over how many things do we have? Well, there's 5 of them, right? I don't think that's any.
Sir, can you zoom out a bit?
Zoom out?
Yeah, just a little bit. Thank you.
All right. So that shouldn't be controversial. Yeah. So, but another way of writing that would be the same as well, how many ones do we have? We have 2 1s and 3 6s. So we could have said, instead of doing 1 plus 1, we could have said, well, 1 times 2, right? And then we could have had 6 times 3 over 5. Nothing controversial there. And then we could have said, well, why couldn't we do it? We can actually say that's the same as 1 times 2/5 plus 6 times 3/5. Right,
Sir, why can't you just do 1 plus 1 plus 1 plus 6? Why do you do all that?
because I'm coming up with the formula that we're going to use here. So I'm just coming up with the formula. So I'm just saying, this is how to calculate an average, and then this, you can rewrite this as the same as how many ones do we have? We have 2 1s, we have 3 6s, right? But then you can divide this 5 into the first term and the 5 into the second term. But so the 1s are the outcomes. What is the 2/5 and the 3/5? So the 1 and the 6 are the individual outcomes, and the 2/5 and the 3/5 are the what? Well, the 2/5 is the probability of getting a 1, right? We had 6 trials, and 5 trials, and 2 of them were 1. So 2/5 of the time you get a 1, right? So and 3/5 of the time you got so these are probabilities. So this is going to be a little hard to write here. I'm going to run out of room. Probability. So what I'm saying is the mean is just the outcomes, the sum of the outcomes times their probabilities. So the expectation, we're going to call it E. The expectation is going to be outcome 1 times the probability of outcome 1, right? Outcome 1 times the probability of outcome 1 plus outcome 2, that should be like a small x, not a big X. Outcome 2 times the probability of outcome 2, and so on. That makes sense? Just based on, and another way of writing this is just the sum of different things. So let's just replace that with just the sum of each individual outcome. I'll just call it xi, and I goes from 1 to all the way to n, I guess. So, right. Does that make sense, guys? So this is just a formula. All you do is just add up the sum of all the outcomes, individual outcomes, times their probabilities. Okay, and what does sigma mean? Sigma means sum of. All right, we'll just leave it at that. So it's a short formula. When you hopefully you read the textbook, does anybody remember what a fair game is? And the expected outcome in a fair game is? Did anybody read the textbook at all?
So I didn't read the textbook, I'm going to be honest.
Okay, so normally in a game you either win or you lose. If the game is not fair, you tend to lose more than you win, or you tend to win more than you lose. If in a fair game, you would expect to win sometimes and lose sometimes, but on average they would even out, and the outcome would be, let's say this game was, you're doing a game that had financial results. A fair game would be one where you win no money. Like the outcome is 0. So that's just a definition. And
Wait, say why is outcome 0?
Because it's not positive. You're not. That's just a definition of what a fair game. When we say game, it's just an experiment. The outcome of an experiment where you have different outcomes. If the total outcome, if the expected outcome, and again, the expected outcome is this formula that I just showed up above. If that equals 0, then it's by definition by definition called fair. Okay, so if the expectation equals 0, then the experiment is fair, then it is fair. Okay, so, right? This will make more sense in a second. All right. The outcomes of a uniform probability distribution. So when we talk about uniform, what does that mean? That would be an example, like an example of rolling a dice, right? If you roll a dice, roll a die, I guess. You have you have 6 outcomes, right? You have either a 1, a 2, a 3, a 4, a 5, or a 6. What's the probability of each one? They're all like
1 over 6.
they're all 1/6, right? So that would be 1/6. I'm just drawing a little graph here, like we did before. They'd all be the same, right? So these are individual outcomes. It's a very small graph there, but that's supposed to be similar to what we did over here, right? This is not a uniform distribution, right? Where this one is. The heights are all the same. They're all 1/6. So in the outcomes of a uniform probability distribution, the fact that they're uniform means they're all the same. They all have the same probability. And the probability is just 1 over, well, we have 6 options for the dice, so it's just, 1 over n, where n is the number of possible outcomes. All right, let's do 2 questions and we'll call it a day. So, question 3. Consider, how did it have to be question 3? What happened to questions 1 and 2? Oh, I see. Yeah, they were on the previous page. Consider a simple game in which you roll a single die. If you roll an even number, you gain that number of points, and if you roll an odd number, you lose that number of points. Show the probability distribution of points in this game. So, you want to do it as a chart or a graph? It's probably easier to do the chart, because normally we do the chart first and then make a graph out of the chart. So let's just do the chart. So, let's call our variable x, whatever, the outcome of the roll. And let's do the points. And then the probability. We'll do that here. Again, in a probability distribution, all you wanted to show is what are the probabilities for all the different outcomes. Right? So here are the outcomes, here are the probabilities. So the outcomes are 1, 2, when you roll a dice, actually, I'm just going to scratch out this x. The actual variable is points. Right? This is the outcome, but the actual variable is how many points are you going to get in the game. So if you roll a 1, according to these rules, do you gain points or lose points?
If you roll a 1, then you lose an odd number.
Okay, it's an odd number, so you lose that number of points. So if you roll a 1, the outcome is -1. If you roll a 2, it's going to be
+1.
no.
Oh.
If you roll an even number, you gain that number of points. So we get +2.
Also, it's +2.
And then it would be -3. That makes sense? Okay, and they're all 1/6, right? Again, these are the points that are awarded, but the probabilities are based on the outcomes. So this is uniform, right? So they're all going to be 1/6. Okay, so this is a probability distribution. You showed the outcomes in both of the actual roll and the actual points that you get from the roll, and the probabilities of each outcome. Okay. What is the expected number of points per roll? Again, well, expected number is the average. We haven't done this game an infinite number of times, but if you did it run an infinite number of times, what would you expect the average result to be? Like per roll. Like, well, let's just do the formula. So again, so we're looking at the sum of all the outcomes times their probabilities. So let's do the first outcome, minus 1. Minus 1 times what? Well, times its probability.
Wait, why minus 1?
What? So this is the first outcome. We're not using this. This was the roll, but the actual variable is points. So the first outcome is minus 1. Okay? So it's this times this. Right? It's minus 1 times 1/6. Right? What we're doing is we're doing the outcome times the probability. So outcome times the probabilities. Okay, but we have to sum them all, right? Plus the second one. Second outcome is 2. Again, it's also going to be times 1/6. Plus minus 3 times 1/6. Plus 4 times 1/6. Plus minus 5 times 1/6. Plus 6 times 1/6. Does everyone see where we're getting this from? We're just following the formula. So on average, is this going to be, what do you think? Is this going to be a positive value, 0, or a negative value?
Oh, wait, it's going to be a positive. Wait. So wait, let me guess. Hold on.
Well, you can actually factor out something to make it a little bit easier. They all have
So
one.
it's going to be a negative answer.
Is it? I don't know.
I think it's going to be a negative.
Okay. Well, why don't you do it? But in fact, when you have 1/6, and why don't we take out a 1/6 out of each one, right? There's a 1/6 in each of these terms, right? So then it's just going to be minus 1. We factor out the 1/6, you got a minus 1, and then here we have a plus 2, and then we have a minus 3, and then we have a plus 4.
Never mind, it's going to be a positive. I missed
there you go. Yeah.
I missed something.
So if you factor out the 1/6, it simplifies it out. That's going to be 1/6 times what the heck is that? Minus 1 plus 2 is 1 minus 1 plus 1 minus 1. What the heck did I do? Minus 4. It's minus 9 is the negative numbers, and plus 12 for the positive numbers. So this is going to be plus 3. Right? If you add all this up, it should be plus 3. So the average is going to be 0.5. So the expected outcome in terms of number of points, even though how can this be negative? How can this be an integer? I mean, a decimal when the possible answers are never decimals. It's that's okay. I mean, that's allowed to happen. If you have if you did this game an infinite number of times, on average, you would get an outcome of 0.5 points per roll. Okay, even though you can't get 0.5 points per any individual roll, you can do it. You can get that average if you did a whole bunch of them. Is this a fair game? Is this a fair game? Sorry.
No, it's not.
No. Why?
Because it's not 0.
Okay. All right. Let's do number 4, and yeah. And this, I think, both these examples came right out of the book. So a summer camp has 7 4.6 meter canoes, 10 5 meter canoes, and 4 5.2 meter canoes, and 4 6.1 meter canoes. Canoes are assigned randomly for campers going on a canoe trip. Show the probability distribution for the lengths of an assigned canoe. So we'll call that variable length, and put the probabilities over here. Probability. Okay, so how many lengths are there? There's 4.6. There's 5.0. There is 5.2 and 6.1. All right, so what's the probability of getting a 4.6 meter canoe? How many canoes in total? 10, 7, 10, 4, and 4. What the heck does that add up to?
It's 21.
You want to try again? I think there's more. 7, 10, 4, and 4. 7.
Oh, I'm sorry, it's 25.
There we go. Okay.
I missed the last 4.
Okay. So there's 7 of the 4. So this is going to be 7 out of 25, right? This is going to be 10 out of 25. This is going to be how many of those? 4 out of 25 and 4 out of 25. So if you were assigned a canoe at random and you did this many, many times, well, on average, what would be the length of the canoe that you would get? So trying to find the expectation, so let's call it EX. So can somebody just tell me what the formula would be? So I don't think this is too difficult. It's pretty much the same thing we just did over here. So it's going to be each outcome times each probability. So why don't you just do that now and tell me what your answer is, and I will do it away from the camera. You just do it on your own. Tell me when you're done. Tell me what your answer is.
So I got an answer. Can I say it?
Sure.
I got 637 over 125.
Okay, what the heck is that? Give me an answer as a...
What does that even mean?
Oh, it's a decimal. It's 5.096.
Okay, I got the same thing.
So it means it's not a fair game.
Yes, well, yeah, you're never going to get an average of 0 because you're giving your canoe, and a canoe has a length. So it's I don't even think that term even applies in this one. But on average, if you are given a canoe at random, if you were assigned a canoe 1,000,000 times, on average, the length of the canoe would be around 5.1. Right, so it's each individual.
I kind of get it. It makes sense.
That's it. That's the whole chapter. I'm going to call it off. I'm going to pause it now because the video is 32 minutes long. So I'm going to stop it.